Hello everyone. Today we will continue discussing the topics in our MOSFET. So we will discuss today what's called constant current and constant current biasing and some other applications for MOSFET. So our topics today or the objectives are investigating the current biasing of MOSFET devices and discussing the MOSFET applications in power switches, in logic gates, and in amplifiers. So let's start firstly, guys, with the circuit that you can see here in front of you. So in this circuit, guys, this is called constant current biasing. Let's see why it's a constant current. So here, for instance, we have a reference current moving in this branch, and we need to calculate the current in the branch here. So let me have the cursor. So if a current is given here in this branch using any current source, we need to find the current moving in this MOSFET M1 according to this connection. So in this branch, which has a current reference here, you can see that the drain is connected to the gate of the MOSFET, and the source is connected to the negative volt here, and the drain current is our reference current. So what do we expect? We do expect to have a similar current in the other branch here. Okay, how this comes? Let's do the analysis together and see what is the current that will flow in the MOSFETs M1 and M2. So start with a certain example. So we have example in the textbook. This example is, we have a pen. So this example in the textbook is example. Just a moment, guys. Okay, yeah, it's working now. So this is example number 314 in the textbook. So the example says, in the circuit shown in figure here, the given data are I reference equals 0.2 milliampere. The V threshold of the transistors is 0.4 volt. However, the factors Kn are given like that. Kn1 equals 0.25 milliampere per V square. For MOSFETs 2 and 3, MOSFET number 2, Kn2 equals Kn3 equals 0.15 milliampere per V square. So these are the given data. The volt here is given. So V plus equals 2.5 volt and V minus equals, for sure, since it's minus, so this will be minus also, minus 2.5 volt. And we need to make the analysis to see how much current is flowing in this branch. So let's say this is the required current here. Okay, let's start, guys, the analysis based on the given data we have. So for this branch here, we know the value of the current. So the current here is 0.2 milliampere. So since we know the value of the current here, we can write here, so I MOSFET number 3 equals, I drain for sure, equals 0.2 milliampere. And you know that any drain current of MOSFET equals Kn times VGS minus V threshold all square in the saturation region. Why we start with the saturation here? Because as we mentioned in the previous class, since the gate and the drain are shorted together, so this means VG, equals VD, or we can say VGS equals VDS, since the drain point and the gate point are the same. So we have VDS equals VGS in MOSFET number 3. So this means it has to be in the saturation region. And this is what we discussed in the previous class. Okay, so okay, so as we agreed again, guys, MOSFET number 3, since the gate and drain are shorted together, so V drain to source equals VGS, and we draw the characteristic of this case in the previous class when we discussed the load and drive MOSFET operation. And we agreed that this type of connection will make the MOSFET working in the saturation region all of the time. So this is going to be now the equation of the second or of the third MOSFET M3. So simply, guys, if we apply now this relation, so ID equals 0.2 milliampere equals Kn, which is 0.15 milliampere per V square, times VGS, which is unknown, minus VTN, which is 0.4 volt, all square. So we will have now one unknown in this relation. So we can say, guys, or we can reformulate the relation from here. So we can say VGS equals square root of I drain divide Kn, and we are discussing now about MOSFET number 3 for sure. So ID3, Kn3 plus V threshold. So this would be now 0.2 divide 0.15 plus 0.4, and this value would be 1.555 volt. So this is the value of the gate to source of MOSFET number 3. Now, if you compare MOSFET number 3 and MOSFET number 2, you will find that MOSFET number 3 has VGS equal to VGS of MOSFET number 2. So we can say for MOSFET M2, VGS2 equals VGS3 equals 1.555 volt. Why? Again, because both of MOSFETs are common source together, so and common gate as well. So VGS3 will be the same as VGS2. So we know now the value of VGS2. Since you know the value of VGS2 and you know the value of KN2, which is equal to KN3 again, so this means, guys, we will have the same current. So if you have a look to the relation here, ID equals Kn times VGS minus VTN. For both of MOSFETs 2 and 3, Kn are the same, V threshold are the same, and they have equal gate to source voltage. Why equal gate to source voltage again? Because it's common gate and common source. So this means by default, any current flowing here in the drain will flow in the drain of M2. So we can say now I drain of MOSFET number 2 equals I drain of MOSFET number 3 equals 0.2 milliampere. Take care, guys. We discussed this many times. The drain current flowing here and the gate current equals 0 in a steady state. So all of the time we consider that at steady state the gate current equals 0. This doesn't mean that the MOSFET do not absorb current to start. So it will absorb current just in the transient period in the beginning. And at steady state, once the MOSFET is turned on, no current will flow anymore in the gate. Okay, because by the end it's going to be a capacitor, and capacitor at steady state will not allow a current, a DC current to flow. So this is a feature of any MOSFET. So guys, according to the connection here, we end up with the MOSFET number 2 will have the same current as MOSFET number 3. And since MOSFET number 1 is connected in series with MOSFET number 2, so this means we will have the same current flowing also in MOSFET number 1. Okay, because as you can see here in the connection, they are connected in series. So we can say now, if we have a branch of MOSFET like that, and connected to a drive MOSFET like that by connecting, sorry, load MOSFET like that by connecting the gate to drain. So the current flowing in the first or in the load MOSFET will be the same as the current flowing in the other MOSFET. Okay. Regarding MOSFET number 1, it's required to get also the analysis, the data of MOSFET number 1, what is drain to source volt of MOSFET number 1. Okay, so in order to do that, we need to make the analysis. So let me write here, guys, what we need here. So find I drain 1. So we got I drain 1 now. Okay, and also we need to get VDS1. And also we need to identify the mode of operation of MOSFET 1. So these are the requirements here in this question. So for the time being, we got the value of ID1. Now we need to get the VDS1 and identify the mode of operation. Okay, firstly, guys, this is the gate of MOSFET number 1. As you can see, gate is connected to ground. So let me write down here for MOSFET M1, VG1 equals 0. So VGS1 equals, you know that VGS equals VG minus Vs. So it's going to be minus Vs1. So the volt VGS1 will be negative Vs1, which is, this is Vs1. So this point here is Vs1. How to get Vs1? We can get Vs1 by means of applying a Kirchhoff voltage law here in this branch. So you know that VDS2 is here. You have VGS2. You have the current flowing. We got the current already here. So how can we get the drain to source? So start firstly with VGS1. So we can say, guys, VGS1 equals, let's start in the other slide. So VGS1 equals, from the current relation, ID1 divide KN1 plus VTN. This is for MOSFET number 1. So this is going to be now root 2.2 divide Kn for MOSFET number 1 was given. Kn1 equals 0.25. So divide 0.25 plus VTN, which is 0.4. So we can get VGS1. So VGS1 is, if you calculate that, it would be 1.29 volt. So we now got VGS1 by means of ID. So we know that ID1 equals 0.2 milliampere after the comparison between the two branches. And based on the current relation in the saturation region, we found out that this VGS equals 1.29. This is based on the assumption of the saturation region. So let's continue based on that assumption and see. We got VGS1 and we mentioned that VGS1 equals minus VS1. So we can say now VS1 equals minus VGS1 equals minus 1.29 volt. So we have the potential of this volt. So this volt here, VS1 equals minus 1.29. Can we get now the value of VDS1, this volt? Simply, if we apply Kirchhoff in this loop or this branch from this point plus 2.5 volt to that point, VS1, so we can have one unknown only, which is V drain to source 1. So let's write the relation firstly. So we can say V plus, which is VDD 2.5, equals RD times I drain 1 plus VDS1 plus this volt, which is VS1. Let's substitute here. So 2.5 equals 8 kilo ohm times 0.2 milliampere plus V drain to source 1 plus minus 1.29. So from here, guys, we can get V drain to source 1. So if you calculate that, you will find that VDS1 equals 2.19 volt. So this is the drain to source. We need to be sure if our calculation based on the saturation region is correct or not. We don't know. If not, so we have to repeat the calculations again in the linear mode. So in order to do that, we need to know the value of V drain to source saturation. So you know that the transition point VDS saturation for any MOSFET equals VGS minus threshold volt. So apply that to MOSFET number 1. So VDS1 saturation equals VGS1, which is calculated before 1.29 here. So 1.29 minus 0.4. So this value is calculate this value and compare it to VGS1 minus compare these values. So 1.29, let me calculate that. See 0.89. So this is VDS saturation. So if you draw the characteristic and assume this is our characteristic here, this is ID, this is VDS. So the transition point here is 0.89 volt. Now, what is the value of VDS1? As you can see, VDS1 is 2.19. So it's located here. So this is VDS1, which means it is located in the saturation region. So our assumption is correct. Okay, so since VDS1 is greater than VDS1 saturation, so MOSFET M1 is working in the saturation region. Okay, guys. So from this example, guys, we got that if you make a load MOSFET connected to the same gate and source of another MOSFET, 100% the other MOSFET will have the same drain current. For that, this is called reference current. So we forced this branch here to have the same current. By the way, whatever, if you have another gate here, it's not connected to ground, whatever, I don't care, but by the end, Since M1 and M2 are connected in series, so by force, the drain current will be the same. Okay, guys. So for that, we call it now reference current circuit. Why reference current circuit? Because according to the current flowing here, you could have the same current moving in this branch. Okay. This is actually very important in uh, electronics control. So we may need it in a lot of applications. Reference current or reference voltages are required a lot in industry. Okay, so this is one of the circuits or application circuits we use in MOSFET. Okay, now let's move to another important application for power MOSFETs, or generally power or low current MOSFETs, which is what's called switches. So, switch, guys, is nothing but a controlled device. So, at the switch of your light at home, so we use the switch to turn on the light. The same, we can use MOSFET as a switch to control the operation of electrical circuits. How this can be done? In order to do that, we have to operate the MOSFET in a certain region. Okay, so what is this region? How can we have the MOSFET working as a switch? So switch means once you apply a certain control pulse, the current will flow from the drain to source. If we compare the three regions logically, you will find that this cannot happen here because the current here is zero or very minor saturation current. So it's not possible to make it as a switch. Also, it's not possible to have it here. Why? Because as you can see for the same curve, whatever the drain to source you have, the current is constant. So this means you don't have like high amount of current. This is number one. And at the same time, you have a voltage drop across the MOSFET. So this is V drain to source, and drain is here and source is here. If you would like to turn a switch on, you need to have this switch as a short circuit. And short circuit means 0 volt. So how comes to have operating point at this point, for instance, and it's 0 volt? It's not zero. So the only region that is possible to be used for the switch application is the linear region. So this is the region that we can use our switch or our MOSFET as a power or electronic switch. How can we do that? Simply, you need to apply a gate pulse in order to work in any of these characteristics. And at the same time, you have to keep V drain to source less than the transition points of V drain to source saturation. So you need to have all of the time the switch unsaturated. Okay, guys, for that, in this kind of applications, when we use MOSFET as a switch, we have what's called desaturation protection. Desaturation protection, normally, when we turn on this switch, you have to connect a circuit here. This circuit is called driver. And this driver, in most of the application, has to be isolated drivers, and isolated by means of optocoupler, for instance. So the gate driver, so this is called gate driver. The gate driver will have isolation. Isolation means the ground of this side, this is ground, let's say power, ground P, and this is ground signal S. So two different grounds. And in between, we have here what's called galvanic isolation. This galvanic isolation, guys, can be in several kilovolts. So it can be 2 kilovolt, it can be up to 5 kilovolt, for instance, in most of drivers. Okay, so this gate driver will provide the pulse, and at the same time, it will sense the drain volt here. So there will be a feedback to detect the drain volt. And comparing the value of VDS, is VDS is relatively high value? Is it increasing or not? If the value is increasing, so this means we are moving toward the saturation region. So what will happen? We have to disconnect the switch for protection. Otherwise, it will work as amplifier. This is another operating region, and for any switch, we don't need to, or we cannot move to the saturation region. Okay, so this is one of the important application we use it in industry. What are the applications of the MOSFET as a switch in electrical power? For instance, I have here one of the circuits. It's a very well-known circuit, and I believe most of you guys know about this circuit. So this is a DC motor. I like to control this DC motor by means of voltage control. So I'm gonna control the voltage applied to the motor here. So this is called VA, or we call it armature voltage. How can we control this VA? We can control this VA by having a MOSFET here in series with the power supply. What will happen? If this MOSFET is turned on, the current will flow from the supply to the motor, and the MOSFET is going to be turned on, which means it's like a short circuit. So you will have very small amount of volt here, which is the V drain to source volt during a linear operation. But this volt is very small compared to the supply volt and the motor volt. So this can be neglected actually. So guys, the volt here will be applied to the DC motor here. Okay, so if I'm gonna draw the operation of this circuit, I'm gonna say firstly apply here VGS. I will apply VGS like that. So this is here a certain period of T, and this is here called T on, and this will be repeated for many cycles like that. So you will have a certain switching frequency for sure. Switching frequency equals 1 divided the period T. And what will happen when you apply a pulse like that to the MOSFET? What will happen is the supply volt here, let's say this is VDC, it will appear on the DC motor here. So we expect that the volt of the motor, let me have another color. The volt of the motor will be applied to, or the volt of the supply will be applied to the motor at the same instance of the gate to source pulses. So this will be the voltage applied to the motor. And so on. So this is here VA, which is the armature voltage here, and the value here, this value is the same as VDC. If I would like to get the average value applied to the motor here, because this is DC volt because it's unipolar volt, so we can say VA average value equals 1 over T integration from 0 to T on this period for the supply we have here, which is VDC dt. So this is going to be now T on divide T times VDC. The term T on divide T, we call it duty cycle. We call it duty cycle. And we can control duty cycle by means of controlling T on. Sometimes we call it pulse width modulation, PWM. Okay, so we can use it to control the output volt across this motor here. Why do we have diode? And what is FWD? FWD stands for freewheeling diode. Why do we have freewheeling diode here, guys? So the nature of this load is inductive load. So the motor has internally resistor, inductor, and EMF. So this is the equivalent circuit of a motor. So by the end, I will have inductance. So if you have inductance in any circuit, guys, if you have inductance and you started flowing current in this inductance, so this means you are transferring energy to that inductance. What the amount of energy you will have, energy for the inductance equals half times inductance value times square of current. So half Li square. Since you have stored energy now in your inductance, you cannot open the circuit. Otherwise, if you try to open the circuit and you have stored energy in the coil will make very high voltage overshoot across all of the surrounding devices. So, in order to protect losing the current in any inductive load, we use such diode. It's called freewheeling diode. So what will happen? Once you disconnect the switch here, the MOSFET switch here, so this is going to be open circuit. So the internal energy stored in the inductance will be start dissipating in this diode and the motor resistance. So the energy will be transferred from the inductance to the resistance through the freewheeling diode. So for that, we call it freewheeling. So freewheeling because it's continue operating the machine current. So the current is going to continue. It will not disconnect from this circuit. So this is a voltage waveform. If you would like to draw the current waveform, you will find that the current waveform, let me draw the current waveform in a different color here. So the current waveform, during the turn on pulse, the current is going to charge. Then during the turn off pulse, the current is going to discharge, and so on. So this would be the shape of the current of this load. So this is IA. This is the armature current of this motor. Okay, guys, for that, the freewheeling diode here in this circuit is very important. Otherwise, it may burn the motor or any other element connected to that inductance. Okay, so this is one of the important applications, guys. And this is going to be one of the projects of this course. So in a week from now, we will announce the different projects you will have in this class, the projects of this year, will be simulation using LT-SPICE or using MATLAB simulation, MATLAB Simulink, or any other simulation toolbox. And then the next step is uh, implementing the circuit on Altium. Why this is important, guys? Because this is what we do in industry. So in industry, start firstly with simulation. Then, if everything in simulation goes well, next step is gonna be implementing this on a printed circuit board, PCB, assemble the component on the PCB. So it will be a PCA, assembled PCB. Okay, we call it PCA. And then start testing this circuit and apply this circuit to your application or to your motor or your load. Okay, so this is the way, guys. So it's very beneficial to know how to do such circuits in our course. Okay, so this is, guys, one of the important applications of MOSFETs. So in this slide, take care that we mention a lot of information since it's application. You may or may not learn electrical machine. I don't know yet. So, or some of you already learned electrical machine. Okay, I believe some of you already had this class with me in the last year, electrical machine. And also, something new is regarding the gate driver. So I believe you have never heard about this before, but if you are gonna make this circuit, you have to design a gate driver. Okay, so this is one of the important benefits you will understand if you are gonna make this project. And in most of projects, actually, you will have gate drivers because by the end you will operate a MOSFET. So by the end, you have to use a gate driver. So this will be a good knowledge to you to understand how to design and make a gate driving for a MOSFET. One more thing, guys. Here we mentioned that this is VGS. Let me now go to the regular color here. So we said this is VGS. We do prefer, guys, the V gate to source to be positive, and instead of 0, we do prefer to have it negative. So I do prefer to make it like that. Why we do prefer to do that in industry? Because a lot of aspects. One of them is when you apply or make a PCB, your ground may not be exact 0 volt. And this may not turn off the MOSFET completely. In order to be sure that the MOSFET is completely turned off, we can apply a negative volt. Let me give you example in numbers. For instance, the gate driver can support positive and negative, and it should be written in the datasheet of the gate driver, like for instance, plus 20 to minus 20. So it can support transition of 40 volt, for instance. So what you can do is you can have, for instance, a gate volt of plus 20 and minus 5. You can have it, for instance, plus 30 and minus 5. You can have it plus 20 and minus 12. Okay, so minus is important to be sure that the signal is, or the MOSFET has been completely turned off during the desired off periods. Okay, so this is very important, guys. And the higher the value of VG, as you can see here from the application, from the characteristic here, the higher the value of VG, the higher the current you can have in your MOSFET. So the same MOSFET, if you have higher voltage, VGS, you can have higher current in the power circuit. So 100%, if your driver provide 20 compared to 30, so 30 will provide more current compared to 20. Provide more current means support more current to flow in the circuit. Otherwise, if it is not supporting that current, it may burn the switch. So this is the idea, guys. So we do prefer, especially in the power application, to increase the positive of the gate to reach to the maximum current, the maximum capable current of our MOSFET we need in our application, and at the same time to have a negative volt applied to the MOSFET in order to have, or in order to be sure that the MOSFET has been completely turned off. Later on, we will discuss together more detailed about the driver when we will make one class to discuss the projects and how you can design these topics in the project. So we will elaborate more in how can you design your gate driver and perform the MOSFET operation in the linear region. Okay, so this is one of the important applications we use it in electrical power in our market. So this circuit here, guys, is called DC to DC converter. This is called DC to DC converter. Okay. From this type of converters, guys, you can have a lot of other application like what's called switched mode regulators. Switched mode regulators like buck converter. So switched mode regulators like what? Like buck, like boost, like buck boost, like chuck converter. So these are very well-known types of converters. We use it in industry. So boost converter, especially used in photovoltaic application to step up the voltage, the DC voltage. Buck is used to step down the voltage. Chuck or cuck converter. So sometimes we pronounce it cuck converter or chuck converter according to the author of this or the inventor of this topology. So this chuck converter can make both of functions, step up or step down. So it's called step up down DC to DC switched mode regulator. Okay. And in all of these switched mode regulators, we will have the part of the DC to DC converter. So the DC to DC is our MOSFET along with the control circuit. And again, the control circuit 100% will include the isolated gate driver. Okay, guys? And also, this gate driver will get the pulses from any microprocessor or microcontroller circuits. Okay, so this is a complete power electronic circuit and its control. Okay, so this is one of the interesting applications of our MOSFET. Here we have a different circuit. It's used for controlling the motor speed and torque. This is called 4-quadrant DC chopper. So the first one here, we call it, this is DC to DC converter. It's DC chopper as well. However, it cannot provide voltage in negative sign. So here, if you have for our motor volt and current here, so if this is V and this is I, so this circuit can allow a current and voltage flow in this quadrant only. So we have 4 quadrants: positive volt, negative volt, positive current, negative current. So this is a single quadrant. This circuit is a single quadrant because it cannot have volt in negative sign and current in negative sign as well. So the current will be all of the time, as you can see here, it's going to be positive either through the MOSFET or through the freewheeling diode. If you need to control this motor, and controlling motor means reversing motor direction, okay, controlling the motor speed, reversing the torque of your motor. So all of these are called different quadrants So we have 4-quadrant operation of electrical machines. So if you have a DC motor like that, the very well-known circuit used for 4-quadrant operation is this circuit. It's called, we call it in industry, guys, H bridge or full bridge converter. Okay, so it consists of 4 MOSFETs with anti-parallel diodes, as you can see. The concept of this circuit is if you turn on Q1 and Q4 together, it will provide the current flow like that, which means the positive of the supply will be connected to the motor terminal here, and the negative or the ground of the supply will be connected to the motor terminal here. So this is now positive volt. How can you do that? By turning on Q1 and the Q4. So if you turn on Q1 and the Q4, this is a gating pulse for IG1, and the same is for IG4. So what will happen? So the current will start charging, and you will have applied volt in positive sign, as you can see. So this is the output volt. You have positive volt here, and the inductor of the motor is charging. Here, in this interval, we turn it off the MOSFET, and you have stored energy in the coils inside the motor. What will happen is the current will continue discharging in the same positive sign. So same positive sign means current flow is still in this direction. So if you find the current flow in this direction, so this has to be, guys, in the direction of Q4 and through diode D2. So if this is IG1, IG4 will not be only this positive part or this interval only. IG4 will be on all the period, all of the time. So if Q4 is on all of the time of this cycle, so from here to here, Q4 is working all of the on time, or all of the forward time, all of the forward time. Okay, so let me draw that in a different color. So in this case, the stored energy here will move through Q4, the MOSFET, and return back through D2. And if this happens, the volt across the motor will be 0. But this is not the case here. Here, the volt is negative, which means we turned on the other MOSFETs. So this is another technique, guys. So we can have a short circuit through the MOSFET and diode to dissipate the energy and have 0 volt at this interval. So instead of that, we will have volt like that, guys. So V on and then 0 for this period. So this will be V, and this is here 0. So this is one technique. So let's say this is technique number 1. This is here technique number 2. If you compare the output volt of the two techniques, you will find that during a complete cycle, which is from here to here, so the current is going to be the same. No change in the current, because the current will discharge either through the other MOSFETs in the other operating region, or through the diode. So the current will flow. No problem with the current. The only difference will be now in the volt, guys. So what the difference in terms of volt? The difference is you don't have negative volt in this part, which means the average volt is going to be higher in the first technique. Why? Because here you have positive area only. So the average during one complete cycle will be higher than the average compared to this technique, because here the negative part will reduce the overall average volt here. As you can see, guys, this is the average volt here in this case. But here it would be higher because you don't have negative sign. So we have two techniques actually. Okay. So the technique I mentioned here is technique number 2. The waveform here for technique number 1. So this is IG1. Let me go again to the other color. So this is IG1. This is IG2. And IG4 will be the same as IG1 in the technique number 2. So let's say this is technique number 2. So you have to know the difference between these two techniques, because this is going to be also one of the projects in our class. Okay. So IG4 here for technique number 2 will be the same as IG1. But here IG4 will be on all of the forward time. This is for technique number 1. Okay. And technique number 1 is preferred because it will provide more voltage. Okay. So we discussed now the forward operation. Forward operation means plus volt and plus current. What about the negative voltage and current? Let me keep this one and take another slide. So for the backward or let's say opposite direction, okay? Let's say negative voltage. If you turn on Q2 and Q3. So when you turn Q2, this means this ground point will be connected to that point. So this will be ground, or let's say our negative. Through what? Through Q2. And the positive terminal will come through Q3 and flow the current in this direction. So this is going to be positive, and the current flow is here. This is the current direction. If you compare this volt and current direction, guys, you will find that it is both negative volt and negative current. So negative volt and negative current means we are working here. This is V, this is I, so we are working here in this quadrant, okay? Or sometimes, guys, we have it like I here and V in the horizontal x, and this is called now third quadrant. Okay, so in the previous slide, if you apply this technique of the waveform, we had positive volt and negative volt and only positive currents. So if you draw the IV, so here I is positive and volt has been reversed in technique number 2. Okay, so we are working here in this region, these two regions. So this is called first quadrant and second quadrant. Okay, but now here in this technique, during the first period, if you use the first or second technique now, whatever, you have Q3 and Q2 turned on together, so you have negative volt and negative current. If you have in technique number 1, which means V will be 0 and current will be negative. So you are still providing the same direction of current. And in this case, the Q3 will be the current is flowing in this direction. So diode 4 has to be turned on. So Q2 and D4 will be on. Okay, so here Q2 and D4 will be on. Okay, if you use the other technique, technique number 2, with the pulses we have in the previous slide, which means you return back again to the other switches. So in this case, the volt will be returned to positive again, and the current is going to be negative. And positive volt and negative current means you are working in this fourth quadrant. Okay, so for that, guys, we call it 4-quadrant operation. Okay, so you need to read more about this for your project and see how can you provide the pulses to your MOSFETs in order to operate the motor in the 4 quadrants. 4 quadrants, it will be very clear to you the first and third quadrant because the motor speed will be reversed. Because for a DC motor, speed is proportional to volt. If the volt is negative, speed will be negative, which means the motor will rotate in the opposite direction. However, torque is proportional to current. So if the current is reversed, the torque will be reversed. Okay, but torque reversing torque is not visible to you in the motor operation because it will just reverse the power flow. So instead of having motor, it will be generator, and this can be, for instance, happen in electrical cars when you go uphill and downhill. So when you go downhill, you don't need to provide any energy for the motor because you already can get the wheel motion and generate power and charge the battery during downhill roads. Okay, so this is called regenerative braking. And the regenerative, the torque will be reversed and the motor speed will be in the same direction because you cannot move the car to backward. In this case, you need to continue moving in the same direction. So torque will be reversed only, but this is not visible, not cannot be visualized to you. Okay, but uh, uh, voltage reverse or speed reverse is visible because you will see the motor rotating in the opposite direction. Okay, so this is regarding the 4-quadrant operation. So all of these guys in this electronic circuits we use now, this circuit or that circuit, all of these are MOSFET as switch, and MOSFET as switch will be in the linear mode. Okay, how can we control it in the linear mode again? We have to be sure that V drain to source is less than V drain to source saturation and apply the gating pulses with the voltage we need in order to allow the higher current to flow in our circuit. Okay, so this is the first thing here. Another thing is we can use the MOSFET in logic circuit gates. I do believe we discussed in the previous class the NOT gate operation. Here, we can use it also in another logic gate operation. So this is called, guys, NOR logic. NOR logic. You know that OR logic is like that, and NOR we just invert the output. So if this is V1, this is V2, this is V out, what will be the logic levels we have? You know that for any ORing, OR is like adding, guys, correct? So if you have one and 0 for OR gate, it will be 1. If you have 0 and 1 for OR gate, it will be 1. So we like adding the logic inputs together, okay? And NOR is going to be the opposite. So we make like OR, then not gate after the OR gate. So if you have any of the inputs active high, the output will be active low. So as you can see here, any of the inputs, so this is active high, so the output is active low. This is active high, so the output is active low. Both are active high, so the output is active low. So it's the not gate of the OR logic. Okay, only the active low, both active low will provide active high. How can you do that with MOSFET? Simply if you have this MOSFET parallel configuration. So quickly, if you apply a 0 volt here and 0 volt here, so this means the output here will not see the ground because it's open circuit. These two MOSFETs will be in turn off mode, and no current flowing through this resistor because no connection to ground. And in this case, the same volt will appear here in the output. So this is active high now. So this means, guys, if you don't have current flow in the circuit, V out will be the same as VDD all of the time. And if you don't have current flow through the MOSFETs, means the MOSFETs, one of the MOSFETs or both of them are off. For that, sorry, if you like to have active high, both of them have to be off. For that, you will find only if you have 0, 0, you'll have high. If any one of the MOSFETs now is working, this will provide a current flow to the ground, and this volt now will be only the value of V drain to source. And V drain to source in the linear mode, guys, will be very small, which means it will be now in the active low region. So as you can see, if any of the MOSFET of both of MOSFETs are on, the output will be active low. So this is the logic gate application of the MOSFET. And as you can see here, guys, this is also in the linear mode. So it's the same as the switch application. This is also another logic circuit, which is in the MOSFET as inverter. How can we do that? By the same idea, guys. So if you have here 0 gate, this means this switch will be off and the active high will appear here. If you have active high, so 0 here will provide 1 here. I'm just writing logic, not voltage magnitudes. Okay. Now, if you have active high here, so active high here means this switch will be turned on, and the turned on here, so V out will be the same as VDS, and VDS is relatively small value in linear mode, which means it's gonna be active low. So as you can see, we could invert the outputs. The 0 became 1, the 0 logic became 1, and the 1 logic became 0. So as you can see, guys, this is inverter logic gate. For sure, you need to make analysis to be sure that this is going to be correct or not. Okay? Because this is analog electronics class, it's not digital logic. We are not working with active high or active low. We work with current and voltage magnitudes. So what you should do here, guys, is analyze the performance at different voltage levels. So since this is going to be working in non-saturation region, or let's say linear region, you have to apply the relation of ID with VDS in the linear region mood. And this is going to be the first equation. The second equation you will use is the Kirchhoff circuit equation. And from these two equations, you can get any unknown in your circuit. Okay, so this is another application, guys. And again, this is still working in the linear mode. Here we have an example. So in this example here, we need to determine the current and voltage in digital logic gate for various input conditions. What are the different conditions we have? Consider the circuit shown in figure, guys. So RD equals 20K, VDD equals 5 volt, and if we apply different voltage levels here, V1 and V2, let's see what we will have. So VTN is given 0.8, lambda is assumed to be 0, and Kn is 0.1 milliampere per V square. Now let's apply the logic values and see. So for instance, guys, let's apply the logic values by 0 volt and 5 volt. So we have now V1 and V2. Let's apply V1 equals V2 equals 0. So here in the textbook, he says for V1 equals V2 equals 0, both MOSFETs M1 and M2 are in cutoff mode. So we don't need to make, sorry. So we don't need to make calculations in case of cutoff mode here. Okay, so it's down. So for the cutoff mode, for sure, since both of MOSFETs are in cutoff mode, so this means the current equals, so in case of 0 volt, so if V1 equals V2 equals 0 volts, so VGS equals 0, it means we are in the cutoff mode, and this means ID1 equals ID2 equals 0, and then IR, the resistor current here, will be 0, and this means V out equals VDD equals 5 volts. So we don't need to make like analysis or calculations in this case. So this means, guys, in the exam, if you just would say since V1 equals V2 equals 0, so V out equals 5 volts. You don't need to uh, like make any calculations in this simple case. Okay, now let's move to another case. So for logic circuits, guys, since we have two inputs, we have four different possibilities. As we mentioned, for a logic circuit, we have V1, we have V2, we have V out. So we can have 0, 0, 0, 1, 1, 0, and 1, 1. 0, 0 already, we made it. 0, 1, and 1, 0, we don't need to repeat because one of the MOSFET will be on and the other will be off and will be reversed together, so it will give the same response, which means these two cases can be, by the end, just one case calculations. And the last one is number 1 here. This is another case to be calculated. So we have two cases now to consider for calculation. When one of the MOSFET is on and the other one when both of MOSFETs are on. So let's go firstly with if one of the MOSFETs is on. So for V1 equals 5 volt and V2 equals 0, the transistor 1 is biased in the non-saturation region, and we can write IR1 IR equals ID1 because the other MOSFET will be off. So this is according to the circuit, guys. Let me get the circuit here in this slide. So according to the circuit here, guys, so we can say that ID, if this is not working now, so this ID equals IR equals VDD, which is 5 volt, minus V out, which is the same as V drain to source volt, divide RD. So this is the current from the circuit. So V5 minus V out divide RD equals, this is the same drain 1 current, which is from the MOSFET relation equals Kn times 2 VGS. VGS is nothing but V input. So this is V input, which is V1, minus V threshold times VDS. And VDS is going to be V out. So let me write here just to remind you. So V1 is VGS and V out is VDS. Okay. So we just substitute in the MOSFET relation between ID and VDS in the linear mode. Why again, guys, in the linear mode? You don't need to calculate in the saturation mode because you know that this application needs linear operation of MOSFET. Okay, for sure you can start assuming in linear in saturation operation, but by the end it will not work with you. So from the beginning, you know that this application is for linear mode. Okay, so we can substitute now in the relations and get our numbers here. So solving the output voltage V out, we obtain V out equals 0.29. So we have now a quadratic equation. You will have two solutions again. One of them will be acceptable and the other will not be acceptable. You can figure this out from the numbers. So if V out or V drain to source is relatively small in linear mode, so this will be the acceptable solution. So as you can see here, V out equal 0.29 volt. So this is a volt we have now, which is V drain to source. And you can calculate now the current. So you can say, substitute in this part of the relation and get the current. So the current is going to be 0.236 milliampere. This is for MOSFET number 1. For sure, we don't need to repeat this for MOSFET number 2, guys. Only you can do that if the two MOSFETs have different like parameters. Okay, so here in this equation, he started replacing the two MOSFETs together. Okay, let's go back just one slide here to see, guys. So we have Kn, VTN, the same, RD the same. So everything is similar. Sorry, so he didn't repeat. So he said that for the opposite operation, it will be the same. Okay, so this is what we described. So from this line, guys, we have the second case, which is if both of them are 5 volt. So both of them are 5 volt. So we can say now the total current equals ID1 plus ID2, which is 2 times ID, because we have two identical MOSFETs. Okay, so we can say 5 minus V out divide RD equals the same equation, which will be here the first current and the second current. And as you can see, guys, V1, V2, VTN, VTN, V out, V out. So it's going to be the same. So we can say 2 times this equation. You don't need to repeat by this way. Okay, so he solved here the equation again. And again, since we are working in the linear mode, we expect that V drain to source will be very small value. So the accepted solution here was 0.147. So this is the output volt or V drain to source. And he calculated the current of IR. Sorry, guys. So again, we substitute in the relation here, guys, and got the value of V drain to source, which is gonna be now 0.147. And again, this is quadratic equation, so you will have two solutions. One of them will be accepted, and the other one is not accepted. And we select the small value because this is in linear mode. Okay, and substitute again in the current to get the current value. So let's summarize what we have discussed today. So we discussed today, firstly, the application of the current reference, and we could see how can we duplicate or have a similar current in another branch using MOSFET circuits. And the second thing is one of the interesting and important applications we use it for MOSFET, which is switch, using MOSFET as a switch in electrical power applications. And another application is the digital logic applications. So we will stop on this point here. Next class, we will continue discussing another application for the MOSFET, which is a small signal amplifier. Thank you, guys, and have a nice weekend.